Hi, welcome to Earth Science Chapter 7, looking at what geologists would call structural geology, looking at crags, cracks, and crumples, the mountain building, and geologic structures. So as we get into this chapter, we're going to be looking at a couple of different things, but they're all going to be related to mountain belts. Now, the prefix oro means mountain, so we have these orogens of geologic mountain belts. And so when we start looking at these rocks, if you had to answer a question at the end of this, what would be the Greek word for mountain belts? We would definitely want to pick something that had oro, telling us it's the Greek for mountains, and then genus as in origins. And so when we start looking at orogenies, the formation of geologic mountain ranges. And so some other terms you may see in this chapter are something like deformation, where we're deforming a rock, bending a rock, or breaking the rock, or causing the rock to flow. Now, there's a number of different ways that we can cause these deformations or deformations. The first one is to have a crack in the rock, and we call a crack in the rock a joint. This may indicate where we have some weathering or a weakness in the rock. If we had some movement along that crack, along that joint, we would call it a fault, and we could actually measure the displacement. Finally, we can have these rocks that were typically horizontal layers getting bent up or bent down, and this is known as a fold. And as well as we already talked about foliation in our chapter on metamorphic rocks. So when we start looking at some of the major mountain belts of the world, we definitely have the Appalachian Mountains here in eastern United States, the Rocky Mountains in Sierra Nevadas. We also have the Ozark Uplift, and we'll look at this area a little bit more closely as it's directly related to us. And then I've already made reference to the Andes Mountains in South America, the Alaskan Range. This whole belt is called the Cordilleran, and that's a term I may use. We've also talked about the Himalayan Mountains, which is located north of India, south of China, right? It's the two continents or subcontinents are colliding. Some other ones that we have looked at, we've looked at the Alps a little bit, and there's obviously a number of other areas that mountain ranges that are listed here on this map. So when we understand a rock that has undergone some displacement, rotation, or distortion are the three different ways that you can deform the rock. So if you were to ask, what is a fracture where there is no displacement? So again, a crack where there is no displacement, that would be one of those items. So if there was displacement on this joint, then we would call it a fault. And we can usually match up sedimentary rocks from one side to the other and figure out the orientation of this crack and the movement of this. And we use this usually using a term called strike and dip, which talks about the orientation of that surface and the amount of that surface from horizontal. And that's what strike and dip is. Those of you in lab, we're going to be dealing with this a little bit more. And in this image, we can see that we have the rock on the left, which is older, which is underneath, and it got pushed up relative to the rock on the right. We'll usually use these little arrows to tell us which direction these samples have moved. Some of these samples are no longer horizontal. We learned that sedimentary rocks formed in horizontal layers in our chapter on sedimentary rocks, and sometimes these rocks get tilted. And again, we can look at the amount of tilt and the direction of tilt, and we can describe that on a geologic map as strike and dip. But we're going to be dealing with this rotation, this movement of this material around an axis. And then finally, we can have rocks that are crumpled, bent, and we call this distortion. A change in shape, where we can take rocks that were nice horizontal layers at one time and then get them to be bent. This would be a great example of the samples. So which of the following is a component of deformation? Well, we just got done saying it was displacement, rotation, and distortion. Movement, tilting, and bending of shape. So in the user guide, there is in the SmartWorks area of the textbook, there's a student guide that talks about some of these different animations and how these rocks can be folded. Some terms when we start looking at these folds, the line that would separate either side is called the hinge line, and then we can look at each side of this fold as a limb, and we can look at the orientation of these limbs, and there's a number of different features, so I would encourage you to go to that animation. When we start looking at the when we start looking at the strain, the stretching of the samples as a result of the force put on or stress put on, what we're going to start off with is a fossil shell called a brachiopod, which can be found here in Missouri. We're going to be looking at this box for our frame of reference. And so the first type of strain that can occur is this elongation associated with stretching. This is going to be associated with pulling apart. You can already imagine what type of forces would be involved in this stretching and these pressure pulling apart from one another. We can also shorten or contract, and this is going to be associated with this squeezing action. The third one is a little bit you may not be as familiar with, and this is called shear stress, where we're going to have this pressure pushing at an angle and causing some of the force to push in one direction, some of the other force getting pushed in the other direction. And so we can see this brachiopod has undergone shear stress. Rocks can behave either brittle or plastic. And if we start looking at brittle deformation, this is a good example of this plate cracking and breaking apart because it's very brittle. And so in this image here, we can see that this rock has undergone some brittle deformation. It caused a joint that moved apart as a result of breaking very quickly. We can look at plastic deformation. Plastic in this instance is referring to a sample that is able to bend, and then you can actually keep that, it will hold its shape after it is bent. And your book uses the example of a dough that has been deformed by the weight of a geology book being pushed on it. So what are some of the different factors that are going to cause different types of deformation? The first one is temperature. My classic example of this would be to use a candy bar. Think of a Snickers candy bar. If it was warm on a hot summer day, it's going to have no problem bending around. But if you took that same candy bar and you threw it in the freezer, what's going to happen if you took it out? It's not going to bend at all. It's going to undergo brittle deformation. Since temperature and pressure are very closely associated, a change in temperature is going to be very synonymous with a change in temperature. The third type of deformation is the amount of the deformation rate. And this is when a material undergoes a sudden force, it is subject to brittle deformation, but if we apply the force very slow, it's going to be plastic deformation. So here's an example of some silly putty. And if I apply this force very quickly, it snaps apart. But if I apply that same force over a slower period of time, it's going to bend. Again, quick, it breaks, slowly, it's going to bend. So when we start looking at this, any type of forces, I do want to talk about the amount of force, and that is known as stress, the force applied to a material over a unit area. These forces can be, this force can be compression, pushing together, tension, shear, or we can apply pressure, the same amount of energy in all directions. And we've looked at water pressure would be a really great example of this, where the force is exerted in all directions. So when we start looking at compression, we see that we have a convergent plate boundary here, it looks like, looking at two continents smashing together. The great example that I would give on this would be looking at something like the Himalayan mountains forming right now as two plates are converging and applying compressive stress. And again, if you'd like to know more about this, there is a great video on the student site looking at the continental collision compressive stress. If rocks are being pulled apart, similar to what's happening in Africa or the southwest part of the United States, where these rocks are getting pulled apart, this is going to give us this stretching taking place. If we take a look at the southwest part of the United States, we see the basin and range topography, where when we start looking at this, this region, we end up with these high areas and significantly lower areas. Other parts of the world may refer to these as Horst and Grabens, which literally means cradle and grave. Rivers try to maintain their course. We'll talk more about rivers later this semester, but as rivers are trying to maintain their course, if we have these areas that are significantly higher up the open range, what's going to happen is these rivers will try to cut through the ranges and try to maintain their course and shift from moving from side to side to cutting down. And then we have shear stress. A shear stress develops when one surface of the object is sliding relative to one another. And again, we've already talked about pressure, and we have rock pressure as well as water pressure, air pressure. Again, all of these are pushing the forces in all directions. And so as these rocks are going to experience this deformation, we have some examples here. Again, I can't emphasize enough that student site has these clickables where you can actually go through and look at these animations. So when we start looking at these animations, again, we can start to see these cracks or joints. Again, a crack without deformation is associated with a joint. There's no movement on either side, and weathering can exploit these joints. These can be smaller, or these joints can allow water to infiltrate in, and then when water freezes, it'll expand those joints. When we start looking at the faults, there's a number of different types of faults. And again, the student site has these animations again for looking at these different types of faults. But a fault occurs whenever we have movement along one of those joints. And so when we start looking at these faults, the slipping or sliding movement associated with these faults can trigger earthquakes. We'll talk next chapter a lot more about earthquakes. Now, if a fault moves up or down relative to one another, it's going to be called a dip-slip fault. And there's three different types of dip-slip faults, and the first one is called a reverse fault. When we start looking at a reverse fault, a reverse fault occurs where along that fault, the hanging wall moves up relative to the footwall. So what is this hanging wall that you've talked about? The hanging, well, in order to talk about hanging wall and footwall, these were mining terms, And along this fault surface, these cracks would allow potentially fluids to build up, in particular things like metals. And so many times miners would go through and mine these faults. In this area, we have the St. Francis, we have the Bonne Terre fault, which is an area that miners would go and collect some of the galena, and they followed that fault surface down. It was right at the surface in this area, so it was called good earth, and that's why we have the town of Bonne Terre. It's still exposed here in the St. Francis State Park, just north of Bonne Terre, where you can actually see this fault extruding at the surface. But in order to talk about these surfaces, we don't want to just say the west side and the east side, because these faults can have some curvatures. We can't say the left side and the right side, because from the screen, this is my left, but if I were to turn around, this is my left. And so I can't talk about this side and that side depending on which face I'm looking at. So we use the terms footwall and hanging wall. And so if we take a look at this fault, I always recommend drawing a person in right along the fault. And as you can see here, they have done that much better than my little stick figure. But the side with the head is called the hanging wall. It's hanging over their head. And this was a real important feature, because if you were scraping away the top of this hanging wall, or if you were mining along this fault, you would not want these rocks to fall on you, so they had to go through and scale off and clean off the top of that fault surface. The footwall is the side that has your feet. And in this case, the hanging wall moved down relative to the footwall. This is a new type of fault called a normal fault. If the hanging wall moves up relative to the footwall, it is going to be a reverse fault. If the hanging wall is more horizontal than it is vertical, and again, 45 degrees is that cutoff, but if we had some rocks that are real close to horizontal, what can happen is these rocks can slide on top of one another to create something called a thrust fault. Both thrust and reverse faults are associated with compressive forces. Normal faults are associated with tensional forces. And so when we start looking at these normal faults, the hanging wall moves down relative to the footwall. So what type of forces is going to occur that are going to cause these rocks to get pulled apart and cause the faulting to occur, normal faulting to occur? When we start looking at dip-slip faults, the hanging wall moves what relative to the footwall? When it moves up, well, this is going to cause some compressional forces. Again, this side is the hanging wall. This side over here would be my footwall. We can actually measure this orientation of this fault surface from horizontal, and that tilt is known as the dip. And if it moves along that dip surface, it is a dip-slip fault. Now, if the movement is not along the dip-slip, if it's moving parallel to the strike, we call these strike-slip faults. As you would expect, these are occurring at transform plate boundaries. Now, when we start looking at these strike-slip faults, these can be left lateral or right lateral. If we take a look at this person here on one side, and they're looking across, this area right here appears to move to their left. And you may say, well, what if I was on the other side? Well, if I was right at this dot, at this X, it looks like the person on the other side moved to the left. And so it's still a left lateral displacement strike-slip fault. Similar here, we can also have a right lateral displacement. From this person's perspective, looking across the fault, it looks like this X moved to the right, or if I was standing at the right, at the X, it looks like the person in the green shirt there moved to the right. So this image would be a right lateral, this image would be a left lateral. Now, in many cases, you're going to end up with potentially a dip slip component and a strike slip component. But how would you know about any of these components if you were actually looking at the field instead of these cartoon block diagrams? Well, there's a couple of different clues that geologists can use to try to figure out where these faults occur. And again, the importance of this would be looking at things like earthquakes, potentially trying to find some mineral resources. And so there's a number of different applications that we have outside of just trying to figure it out. But the first thing that we would see is if the entire landscape has had some movement associated with it, it would create an offset on the ground. Again, if we start looking at this area, and if I have one cohesive unit here, and if I were to slide this side up, we would have some offset. This side would be higher than this side, and we call this a fault scarp. As right along the area the rocks are crushed, that would be some broken up bits of rock called fault breccia. As these rocks are sliding past one another, they can become polished to create something called slick and slides. You can end up with slip lineations or little lines or grooves associated with these faults. And you can also have a fault trace, a line of intersection of the ground surface and the fault. And so one of the classic examples of this fault, a strike slip fault would be the San Andreas fault. And so we can see that this river, this creek bed, and this creek bed were once connected. So if I were on this creek bed, which direction does it look like it moved? It looks like it moved to the right. So this would be a right lateral strike slip fault. Similarly, if I was in the headlands of this creek and looking down, it looks like it moved, the lower portion moved to the right. So when we start looking at this strike slip fault. Now, again, not every rock is going to break with brittle deformation. If we apply plastic deformation or bending deformation, we can create rocks that have folds. There's a number of different types of major folds. The one that we're going to start off with is something called an anticline. And so this occurs where the rocks are getting smashed together to create this arching bend called an anticline. And when we start looking at each bend, each side is called a limb. And so we've got this limb and this limb collectively combined to form this anticline. And with an anticline, the rocks dip away from the hinge line, the boundary that would separate this curve. Similarly, we could also have a syncline, where the rocks, the limbs dip towards the hinge. If we only had one fold, we've got a monocline there. We could also have a dome and a basin. Now, a dome would be occurring if this set of rocks were tilted up to create this bullseye pattern, this rainbow pattern, but instead of being more like a bunch of lines, what's going to happen is it's going to look, we start looking at this rainbow pattern in cross section, but it would also look like that rainbow in side view. So what are some examples of plastic deformation where you're creating bends? These anticlines would be a good example of one of those. And these bends can be symmetrical, both sides looking the same, or one side can have more of a dip than the other. But what we have here is an anticline. It looks like an arch. In side view, it does definitely look like an arch. If we're looking at it from the this one of the faces. If we look at it from the side view, we'd see that it would look like the rocks are not tilted at all. Here's our syncline. It looks like a trough. And we're getting some differential weathering here, showing that this layer of rock is sticking up a little bit more because it's not as weathered away. When we start looking at this monocline, one cline, the next type of modification that we can have to these folds is these folds can plunge. And so if we have an anticline like this, if this is tilted into the earth or plunging into the earth, and this is where the hinge line, that line that would be a horizontal line right where this arch is occurring, is also having some tilt associated with it. And we can look at how much it's dipping or plunging. These plunging folds will create a U-shape on the Earth's surface. If we had a doubly plunging anticline, we would call that a dome. And so you can look at any of this dome, it may look like in side view, more like an anticline, but in both directions. When we start looking at a basin, it looks very, very similar to a syncline in, again, in two directions. When we start looking at these rocks and trying to figure out which rocks are older and younger, with some very rare exceptions, rocks dip towards the younger beds. And so if we start looking at any one of these folds, if we unfold this, the layer on the outside would be the youngest. And so if we started looking at this anticline here, the oldest layers would be right at the hinge. And if we folded this back in place, the stuff on the top would actually be this darker brown unit right here. If we start looking at a syncline, the rocks are still dipping towards the youngest beds, but the stuff would be oldest in the center. When we start looking at domes, the rocks are youngest on the edges, oldest in the center. And basins, rocks are youngest in the center, oldest on the edge. Again, rocks dip or tilt towards the youngest beds with some, in many of the cases. So what type of fold would dip away from the hinge? So folds are a result of compression. Maybe we had two continents colliding, as is the case of the Appalachian Mountains. And so if we take a look at a map of the Appalachian Mountains, this is a 3D map, and you can sort of see that these rocks are buckling up as a result of these two collisional forces. But you can see in side view that it does in fact look like a series of rainbows. And again, this compression. Inside, if we look at the other side, we don't see that compression there. We could also apply shear forces, gradually shifting one part of the rock body relative to one another. These layers can move up as they're being confronted, as they're being pushed together. The reason why we call the low angle dip slip faults thrust fault is because it's thrust on top of one another. And so you actually get the same unit of layer multiple times. Then we can have slip on the fault, causing the basement to move upward relative to the neighboring rocks. So some examples of these folds. Looking at this in nature, we have this aerial view of this plunging fold here, this anticline. If we take a look at a geologic map of the state of Missouri, we can in fact see that we kind of have this bullseye pattern. And if we take a look at the rocks In side view, we can see that the rocks are tilted away from the center. That's telling us that this rock is moving, tilted away from the center. So this would look like this dome. Here's a zoomed in area of the St. Francis Mountains. And again, we still have these rocks tilted away from the center. But as it turns out, we here in, this is the only portion of Missouri that really has exposures of one of these geologic domes here in the state. An example of one of these basins would be the Michigan Basin. If we look at it in side view, it looks very similar to that dome. The lower portion of Michigan, that glove portion of Michigan, kind of looks like that southeast part of Missouri. The difference is in side view, instead of having these rocks tilt up towards the center, it dips down towards the center. When these rocks are undergo stress, you could have these rocks become metamorphosed, in particular created a foliated metamorphic rock. We've already talked about foliated metamorphic rocks in our chapter on metamorphic rocks. So when we start looking at orogenies, again, the Greek for mountain genesis, this is a process of mountain building, and this can occur at subduction zones, at collisions, which are both convergent plate boundaries. This can also occur as a result of accretion of exotic terrains, and then also at divergence, at rifting, and we'll talk about each one of these as we close out this chapter. So when we start looking at mountain belts associated with subduction, again, this is a convergent plate boundary where the subduction is going to cause the mountain on this side to thicken and create this uplift where this area is getting lifted up. If we had two continents colliding, as we can see here, India and China occurring, you can almost see where that buckling is taking place and creating a very buoyant region in the middle. Remember, continental crust is less dense than ocean crust, and so as a result, not only is it pushing up, it's also pushing down. We'll call that isostasy. We can also have accreted terrain. Now, if we take a look at the Pacific Northwest, we had some island arcs that were in fact fully subducted into the continent. And since continental crust is less dense than ocean crust, what's going to happen is it's going to stack up. It's just going to build up as that subduction is taking place. And we call this accreted terrain or exotic terrains. Now, the last type of mountain building is associated with continental rifting. Again, when we start talking about rifting in the mantle, heat is rising up, it's pulling this material apart, and as a result, these rocks are getting pulled apart, which is going to be causing some tensional forces. So much more common to see rifting associated with this, normal faults. And some other consequences of these mountain building, we can form new rocks. We can have rocks under tremendous amounts of pressure reforming different minerals. And then finally, isostasy. This is equal buoyancy. It's what the word literally means, and we can think of that. You may have heard just the tip of the iceberg, because 90% of the ice is below the surface, only 10% is showing. But if we were to remove the top of that ice, the 90% isn't going to stay beneath the ocean surface. It's going to pop back up. It's going to maintain buoyancy. And then finally, we're going to talk about mountain building. It's going to lead us to larger continents, and these continental basement rocks literally are called cratons, which means strength, the core of those continents. And I know we've just got done mentioning those in our last chapter. So when we start looking at what type of rocks are found near mountains, well, as a result of weathering, we have sediments and sedimentary rocks. This pressure building, this is one of the places that we do get metamorphic rocks. And then finally, since these are associated many times with mantle material being solidifying, so we get igneous rocks. So we have lots of all of the three different types of rocks. So I've mentioned isostasy. Your book gives the example of a boat that on the left image here is less dense than the boat on the right. And so if it's less dense, it's going to want to maintain, it's going to stay up. But if we started piling up material or putting more material in this boat in this case, what's going to happen is the boat is going to push down. And so as a result, the more you put on this material, the thicker the crust is going to be. So where would you expect to find the thickest crust? That's right, at the mountains. And so again, the student site does have a nice visual looking at isostasy as well. When we start looking at the craton, these areas are broken into two main portions. The first portion is called the cratonic shield, which is the Precambrian rocks that are usually igneous and metamorphic. But if we have these big blocks of igneous and metamorphic rocks, in some cases we could end up with sediments building up on these to create cratonic platforms. The upper Midwest is covered by this large platform. Here in Missouri, the northern portion, the only exposure of the Precambrian shield would be the St. Francis Mountains. And so if I were making this map focused on Missouri, I'd make sure that I'd also have my little St. Francis Mountains occurring right there. So we can see the shield exposed in the northern part of the United States, but this area right here, this platform, this big flat area, is a result of that cratonic platform. So as that cratonic platform is occurring, well, when we start looking at these rocks over here, it's going to be higher, it's going to be subject to more weathering, and it's going to wash this material into the low-lying region, which is going to create these basins. And so with many cases where you see domes, very near them you see basins. So if you have any questions, please let me know.